So for this big data example then, so the data in either the Excel file or the .text file available on Canvas, called score data, it gives the ratings of 24,365 reviewers for a range of different products. And when the thing says product, what it means is hotel. So you could argue whether or not this really is big data, but it's certainly big enough to be impractical to use things like Microsoft Excel. So I think it's easiest to manipulate, given the size of the data set, to use a proper programming language like R. So that is why I say there, you could argue whether or not this truly is big data, but it's certainly big enough to be non-trivial and informative, and to need something with proper programming functionality like R. Now within this, some of the data regarding the regional affiliation of the survey respondents is missing, and data corresponding to these entries needs to be deleted. So the easiest way to do this is to copy the data from Excel into Notepad and then read the data into R using the command read.table. And then once the thing's been read into R, you can use the command line in R to organize the data as required. Okay, much easier to do this using a proper programming language rather than something like Microsoft Excel that just requires manipulation. Okay, so reading the data into R then, so the easiest way to do this is to save the data file directly onto a USB stick to make the file path shorter. So in this case I've used scores goes to read.table, and then this bit in the speech marks is the file path. So you have to start thinking about where each file lives on your computer. So when I do this on my work computer, the USB drive is drive G, and then I've saved it there as scoredata.txt. And it just means when you're doing this, if you save it directly to a USB drive, the file path is shorter, so it's less likely to corrupt. Okay, you're less likely to make a mistake for whatever reason. So if you're doing this in R, then if you type in scores and press enter, this will just print out the whole data set that you've entered in and the data that R recognises with the word scores. Probably best not to do this given that there's 24,000 observations here. And the next thing you need to do is define the variables one by one. So how this works is that in R you always use square brackets, and then this works like coordinates, row, column. So rating goes to the first column, product goes to the second column, region goes to the third column, region missing goes to the fourth column. Okay, so it's like coordinates, and remember this with the word arc. So you've got the whatever the thing is, and then the first number is row, the second number is column. Okay, so once you've got the data into R, it's easiest to process this in R using the command line, and the first thing you need to do is to delete the entries for the unassigned regions. So this is easy to do in R using the vectorized nature of R and these following subsetting commands. So what this is then when you do this is that rating goes to the part of rating where the region missing variable is less than 1, and similarly for the other two, so product goes to the product variable where the region missing indicator is less than 1, and then again region goes to the region variable restricted to the cases where the region missing indicator is less than 1. And there are some subtleties in terms of how you manipulate the data in this case. Okay, it turns out this is the easiest way to do it. And then you need to tell R to put the data in the right form. So within this, the data for product and region are labels rather than numerical measurements, and R needs to be told this. So in R, the command to do this is factor. So what you would do there is product goes to factor of product, and then the line below that should say region goes to factor of region. Okay, and all you're doing in R when you use this command factor is you're telling R that these variables are labels rather than strict measurements. In terms of analysing data in R then, so as this is a non-trivial problem and things like actually reading in the data for the first time can be a bit tricky, it's worthwhile just to look at the data just to see if you've made an obvious mistake. Okay, so it might sound really simple-minded. Okay, that's not necessarily a bad thing in this instance. Whatever analysis you're doing, whatever you're trying to do, it's always worth just looking at these simple common sense cross checks just to verify that you're on the right lines and you haven't made an obvious mistake. So in this case, what we're going to do is just look at the variable region. So in R, if you type summary of region and then enter, what you get is a list of the labels and then a count of the number of times that these things occur. So what you've got there is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 regions, and so 10 counts that are roughly equal to each other are the number of times that each observation occurs in this factor variable region. Okay, so it's always worthwhile as well whenever you're doing any programming in R, if you're unsure of what something is, if you just get R to print the thing here by just say typing region, you can just look at what R recognizes by the variable region. Okay, so there's some important softer skills here in terms of just these common sense checks. In terms of regression analysis in R, so again it's always worth thinking about how the thing is really working. So think R equals robot, it will do exactly what you tell it to do, nothing more, nothing less. So in this instance what you typically have is these two steps. So firstly, run the analysis, and then secondly, you're explicitly telling the computer to display the results. So when you run the analysis using the command lm, then you're getting it to display the results using the command summary. So the first step, run the analysis. So how to read this? This is a linear model of rating dependent upon the region. That is what the tilde or the squiggle sign means, and you're going to call it something logical here, a.lm, and then in the second step get it to summarize the results. So the command is summary applied to the name that you've used at the first stage. So that name there, summary a.lm, that name a.lm must match exactly what you've called the thing in the first stage. Okay, but this is a very general way of working in R when you have this sort of two steps. First step is a computational step, get the thing to perform some analysis, and the second step, tell R explicitly to display the results. Okay, this is and also throughout this, just remember R is a robot, it will do exactly what you tell it to do, nothing more, nothing less. In this case then, if you use the command summary, you get this table of t statistics, which would be the thing to really look for here. And then within this, the interesting part of this table is the second row downwards. So how you would usually do this, so you're working out what's interesting going from right to left, and then you usually write this down in the Queen's English going from left to right. So the first thing we're looking for here is the p-values that are less than 0.05 from the second row downwards, and these are usually accompanied by an asterisk in R. So here only the second row is important, this second row corresponding to the London Essex region, precisely because there's an asterisk and the p-value is 0.0247, which is less than 0.05. And then if we move from the right to the left, we see that the estimated coefficient is minus 0.064965, which is negative. So if you write this down in the Queen's English, going the opposite way round from left to right, you would say that the coefficient of the London Essex region is negative and statistically significant. Okay, so this will have important bearing on the interpretation of this problem, as the suggestion is that you get generally lower results on average if the respondent is from the London Essex region. Okay, so just to summarise all that then, so interpreting these regression results, the convention would be, again, that it is the second row of this table downwards that is interesting. So this is because you usually fit a constant or underlying average term to the model unless you've got special circumstances. This means that even in the absence of a regional difference, we don't expect the average score to be exactly equal to 0. Okay, and then as we said before in the previous slide, taking the results at face value, there's evidence p equals 0.0247 that the results for those from the London region are lower than for the others. Now this is important again because this is a genuine data problem that comes from an industrial application. So the suggestion would be in this case that electricity and water companies that are based in the London region are systematically disadvantaged by the current system of regulation and the way that the customer satisfaction scores determine fines, precisely because the implication is that if people are subjected to the same set of conditions, they give lower survey responses on average if the respondent comes from the London region compared to the other regions. Okay, and this is significant given the way that this industrial problem is set up and the way that fines are imposed in regional monopolies such as the water and electricity industries in the UK. So one thing I want to sort of show you here is that in this case, because of the special circumstances, it is important to consider reparameterizing the model, and whatever you're doing here, whatever hard maths and computing is involved, just remember that communication is the name of the game. Now this can be quite subtle, and this relates in this instance to, I think, a minor mistake that we made in the actual final published paper. So this was sufficiently subtle to get past 2 professional statisticians. So in this case, the estimated effects of the regional bias can be better presented by reparameterizing the model, which is intended to emphasize, as I say, this communication aspect of any maths and computing that you do. So in order to do this, we can suppress the constant term in the fitting of the regression model, and in R you do this by including a -1 term in the list of x variables. So again, you've got this 2-step process. Firstly, run the analysis. Secondly, display the results. Remember, R is like a robot. It will do exactly what you tell it to do, nothing more, nothing less. So in the first step, you want a linear model, rating related to region, that's what the twiddle sign means, -1, so no constant term. Call the thing something logical here, b.lm, and then summarize results, summary b.lm, exactly what you called it at the end of stage 1. Results that you get should look like this. Now in this case, the p-values on the far right hand side aren't really very informative. Okay, but the thing to watch for here in this example is that you've got roughly similar looking average scores for respondents from each region, and they are slightly lower in London compared to the rest of the country, and that's significant because that reflects the difference that you found on the previous slide. Because the results for different regions are fairly similar to each other, we can have some confidence that you haven't made an obvious mistake. And the other thing to watch for here is that since all these scores are constrained to lie between 1 and 5, indeed all these average scores themselves all lie between 1 and 5. Okay, so there is, in some sense, I think, limited amount of information on this slide, but the main thing to watch for here is that there's no clear and obvious sign of a mistake that we've made at this juncture. Okay, we're getting similar looking results across the different regions. The results look slightly lower for London compared to the rest of the country, and all these scores lie between 1 and 5. Okay, so no obvious sign of a glaring error at this stage. To interpreting these regression results then, so the numerical values should be the same under either parameterization. So this is another common sense check that you want to verify. Show you how to do that in the next part of the lecture. And then how we've done this in terms of the communication, which is always very important. So use the first parameterization to test for regional differences. So in this case, the significant values indicate that London scores are lower than the benchmark score for the East Midlands category, and indeed lower than the other regions. And then the second parameterization is the easiest way to present the estimated average score for each region. So in this case, the significant values, the p-values being less than 0.05 on the previous slide, aren't really very informative. All they do is indicate that in none of the regions is the estimated average rating equal to 0. The numerical estimates obtained suggest only minor differences in the average scores given by customers from different regions, although this isn't formally tested for. Certainly, I think the thing to watch for here is that the results are the same order of magnitude for whatever region, so there's no clear and obvious sign of a glaring error. And the thing to sort of check for, as we'll show in the next part of this lecture, is to show that the estimated customer satisfaction scores should be the same under either parameterization.